Thank you. Good morning, everybody. Welcome to my third lecture on maximal regularity business. So yesterday we have learned about the invention of R boundedness and the fact that maximal regularity is equivalent to R boundedness of the resolvent, or more precisely of lambda times the resolvent. And this is some properties of R boundedness and so on was invented between 15 and 10 years ago. And now if we want to apply this for some given boundary value problem, we have to find a good description of the resolvent. So we have to check if we can find some result on R boundedness like Michelin's theorem, which tell us, yes, this resolvent is R-bounded, this operator is maximal regularity. And this is almost immediate if we have an operator in the whole space. This we have already seen yesterday a little bit. And it's more complicated if the operator is in some bounded domain and we have boundary conditions. So what I want to show you today is a description of the resolvent for boundary value problems. And in some sense, what I tell you today is much older, as we have seen with the machinery of Michelin and so on, that essentially it's the same to understand if this operator is parabolic in the sense that it generates a holomorphic semigroup, so it's a sectorial operator, or to show that it's R sectorial. This is more or less the same. And therefore today I go back in some sense to the Russian school of describing the resolvent of boundary value problems. And this was, in fact, the beginning where I entered PDE at all, because after my PhD, I get into contact with some mathematicians from Moscow, Agranovich and Volevich, and they told me how to compute resolvents. And so today I will talk about maximal regularity. For linear, parabolic boundary value problems. So let me start with an example. And this is a repetition in some sense of yesterday. So I consider the heat equation. So let A be the Laplacian in Rn, which means that the domain of A is WP2 Rn, which is the same as HP2 Rn, as a subset of LP. So I consider this as an unbounded operator in LP. And we want to understand its resolvent. So, of course, this is in Rn. The Laplacian is a very simple operator. It's constant coefficient. So, of course, we take Fourier transform in X. So, for the resolvent, we have lambda times the resolvent, which is defined for all lambda on, in fact, for all lambda which are not negative real numbers, but in particular for all lambda in the right complex plane. This was always the condition, and except 0. And this is an operator with some symbol. And of course, lambda minus Laplacian has a symbol. If you go to Fourier transform, you get lambda plus modulus of xi square. The resolvent gets this in the denominator. So m of xi and lambda. So if I start with the denominator, here I have the symbol of the lambda minus Laplacian. And this lambda here gives me this lambda here. Okay, so this is the symbol of xi and lambda, and this symbol is homogeneous of degree 0. Quasi-homogeneous in the sense that if you take rho square lambda and rho xi, then you get the same value. So this symbol as M is quasi-homogeneous of degree 0 and weight 2. This symbol satisfies the Michling conditions. It's the infinity, of course. It satisfies Michling's condition. Now we can apply the theorem of Michlin, but not in the traditional way. This would say this gives a bounded operator in LP. But in the modern way, this was a theorem by Girardi-Weiss, and tells us this gives us a family of R-bounded operators. So by the Girardi-Weiss theorem, the family of operators, lambda times lambda minus Laplace inverse, lambda in the right closed complex plane except 0 is R-bounded. So this is a family of operators in LP, L of LPRN is R-bounded. And by theorem 211, this R-bounded, this is an R sectorial operator, and therefore, by the last theorem of yesterday, this operator A has maximal regularity with a 0 here, 0 infinity in LP. Okay, so this was repetition in some sense of the machinery of yesterday. And as I already mentioned, in finite time intervals, you can omit this 0. By the way, which I did not mention yesterday, so the difference between MR0 and MR was the fact that U should also belong to LP, not only AU or DTU. And what I did not mention yesterday is if A is invertible, so if 0 is in the resolvent set, and if AU is in LP and A is invertible, then also U is in LP. So if 0 is in the resolvent set of A, which is not the case here, of course, if 0 is in the resolvent set, then you can also omit the 0 immediately. Okay. And okay, so this was a prototype. This was a prototype of a parabolic equation. It's the heat equation. So maximal regularity means I have now well-postness of the heat equation in the appropriate Sobolev spaces. And if you check this, then it's what is the point in this argumentation? The essential point is that I can here take the denominator. This is the point. So I have here no zeros of my symbol. This is the point. And this is the basis for the definition of parabolic problems. And so now I consider a little bit more general situations, and I will fix this situation. So let me make a remark. So the essential, in all this argumentation, the essential property of the Laplacian was that lambda plus psi square is not 0 for if lambda is in the right complex plane, because then I can simply divide by its symbol. And this is the basis of a very classical definition of parabolic problems. So this is the basis for the definition of parabolicity. And this is a classical definition from the 60s. Okay, but for this I fixed the situation. So let M be a natural number starting from 1. G subset of Rn be a uniform C2M domain. for instance, a bounded C2M domain. May also be unbounded, may also be exterior. And I consider and let A of xd and bj of xd be differential operators, differential and boundary operators. Operators of the form. So what I formulate here is the whole theory, and this is a typical feature of the theory, is not restricted to second order. It's an arbitrary order. I have arbitrary boundary conditions. It's not restricted to second order and not to Dirichlet or Neumann. I have maybe fourth order and so on. And so I have a general linear differential operator. So A of xd is the sum, and the order of A is 2m. So I assume from the very beginning that it's an even order. I have some coefficients, and then I have d alpha, and bj of xd is again a general boundary operators, let's say of order mj. J runs from 1 to m here. I have some coefficients of x, and then I have here this gamma 0 d beta. And this gamma 0 was yesterday, it was the trace on the boundary. Yeah? So gamma 0 u is u on the boundary. So I have some differentiation, then I restrict my function to the boundary, and then I multiply with some functions which are given on the boundary. Okay, and so first of all, I introduced this d, which is nothing but minus I and the normal standard partial derivative. So d to the alpha and the multi-index notation is just minus I to modulus of alpha. And this minus I comes from the fact that I want to apply Fourier transform. So in Fourier transform, this d becomes a psi. So partial derivative becomes an I psi, and I want to omit this I there. I introduce this. And okay, what else? We have J runs from 1 to m. The orders of the boundary operators are assumed to be strictly less than the order of this operator. This is, of course, not always the case, but this is the case I treat here. And okay, what about the coefficients? So now I assume some smoothness on the coefficients. Yeah. So A alpha, I assume that A alpha are bounded uniformly continuous in G. And if I have a top order coefficient, so top order is 2m, and I assume that A alpha are L infinity of G, if alpha is lower order. And then I have to assume some smoothness on the coefficients of the boundary operators. So bj beta belong to bounded uniformly continuous of order 2m minus mj being defined on the boundary. Of course, if the boundary is compact, for instance, if I have a bounded domain or exterior domain, then this bounded uniformly can be omitted. But I really need some smoothness on the coefficients of the boundary operators. Okay, so this is my situation. I want to solve this equation. In principle, dt minus a u is some given function, and these are m boundary operators. So I have the order of the operator is 2m, and half of the order is the number of boundary conditions. And as I said, in principle, I want to apply a Fourier transform. Of course, in a bounded domain, this is not possible, but we will come to this later. Nevertheless, I already now define the principal symbol of A and Bj. So the principal symbols. symbols of A. So these are first of all formal differential operators. Bj are defined by, so let's say A0 of x and xi. I take exactly the same sum, but I take only principal parts, and therefore principal symbols. I take the coefficients as they are, and instead of derivatives, I take multiplication with my covariable. And the same for bj0 of x and xi are defined as some beta equal mj. So I omit lower order terms, and I have x xi to the beta. Okay, so this is of course defined if x is in G, xi is in Rn. This is defined if x is on the boundary and xi is in Rn. Okay. And I start with a situation where I'm in the whole space, so then I have, of course, no boundary operators. So if this is defined in Rn, then I can omit the boundary operator, and then I'm in this situation here. And instead of lambda plus psi squared, we have now the principal symbol, lambda minus the principal symbol. And the essential property here was that this does not vanish. And this is exactly the definition of parabolicity. Yeah? So I start with A, so parabolicity of A. So A of xd, the formal operator is called parameter elliptic. And if I consider the instationary problem, dt minus A is called parabolic. If lambda minus the principal symbol does not vanish. For all lambda where we are interested in, so with lambda, well, let's say xi, lambda in Rn times the right half plane except 0. Okay. And of course, x in G bar. Okay. And if we are in the whole space, then this is already sufficient to show that this operator has maximal regularity, exactly by this proof. More or less exactly by this proof. So, of course, now our symbol depends on x. So we cannot simply take Fourier transform. Nevertheless, we can consider this as a symbol in the sense of Fourier multiplier, where now the symbol depends on x and xi. So this is, by the way, if I don't know if you know this is, by the way, exactly the idea of pseudo-differential operators. So this is not part of my lecture now, but a pseudo-differential operator is something like f inverse A of x psi f. This is the definition of a pseudo-differential operator. And when this notion was invented in around 1964 by Ekman, Agranovich, Wyschik, the theory of pseudo-differential operators was also invented at the same time. So this was exactly the same idea. Okay, but I take here the principal symbol, and this principal symbol is of order 2m with respect to xi. So this expression is quasi-homogeneous in lambda xi. And therefore the same argument holds, and we come to to the following result. So now I consider the whole space case. P is Rn. I have no boundary operators, of course. And let A of xd be parameter elliptic. And then I consider the LP realization. And the LP realization. Let's say A index P of A of xd, which is defined in the canonical way. So the domain of AP is WP. I've ordered 2M of Rn. I consider this as an unbounded operator in LP Rn. And AP U is defined as the A of xdu. This operator has maximal LP regularity. Has maximal LP regularity in finite time intervals. So AP is in the maximal regularity class for 0t in LPRN for every t in 0 infinity. Okay, and the idea of proof. So if this operator, so we have 2 points. First of all, we have taken only the principal part. So there are some lower order terms, and I did not care about them in the definition. No? And in fact, they are not important because lower order terms are treated by perturbations. And the other point is that it depends on x. And there I have something to do because I cannot simply take Fourier transform. But if I fix the x, what is called freezing the coefficients, then I can make Fourier transform. So locally at some point, x naught, I can apply the method here. And but this is locally. And now we have some technicalities. So we take a partition of unity, we localize, we take local resolvents, and then we put the local resolvents together. And all the technical stuff is at the end some perturbation result. Okay, so the idea of proof is I freeze the coefficient. So freezing the coefficients. More precisely, I consider what is called the model problem. I consider A0, so the principal part of x0 and d. So the principal part and fixed coefficients for fixed x naught in Rn here. I obtain a symbol which has the same properties here. So we obtain a quasi-homogeneous symbol. Symbol A0 x naught xi. Oh, lambda minus, it's quasi-homogeneous. Yeah? And this can be treated as in this example, which can be treated as in example 3.1. So all these operators are R sectorial. So I have locally a good resolvent, but now I have to take a partition of unity. So the general case, now we take a partition of unity. Unity of Rn. And this is a point, if you take a look in the conditions, this is the point where I need continuity of the principal symbols, because I have to know that in a neighborhood of x naught, this has to be close to the operator when I freeze the coefficients. This is exactly the point where I need this BUC condition. And now we locally solve it, and then we take the local resolvents, put them all together, and get an approximate resolvent. And then at the end, by some standard perturbation result, we get the real resolvent, and use perturbation results. So in two ways, for the difference. So first, for the difference A naught xd minus A naught x naught d. And here we need this continuity. And for the lower order terms again, as well as for the lower order terms. However, these perturbation results mean that I have not the same operator. So for instance, for the lower order terms, we need some interpolation inequalities in Sobolev spaces, which means that I get some shift of the operator. So with these results, one can show in this way, one can show that lambda 0, it was the shift is in, yes, plus A has maximal regularity in the whole interval LP. But I need a shift. This shift comes from the perturbation. I did not need the shift in this example because I had no perturbation here for some positive number 0. Okay, but what means shifting the operator? If I take a look at the equation, this means I solve the equation with the original operator, but in function spaces which have an exponential weight. So this is equivalent, you can easily see. Yeah? So if this has maximal regularity in every interval, in particular in every finite interval, it has maximal regularity. But on finite intervals, exponentially weights do not matter because they're equivalent to the original equation. So the exponentially weight is really, so this means, so for A, this means unique solvability on the whole interval, unique solvability in with respect to exponentially weighted spaces. So I have the weight is e to minus lambda 0 t. So I take, for instance, f t lp. So I get an exponential weight. If you plug this in the equation, you see this is just a shift in the operator. Okay, and in finite time intervals, this exponential weight doesn't matter because it can be estimated in both sides by constants. So on finite time intervals, we can omit the weight again. And if you look in the literature, you will see that sometimes, or mostly the formulation is that this is the statement of the theorem. Yeah? There exists a shift, that the shifted operator has maximal regularity in the whole line. Okay, so this was the simple case where just essentially, apart from technical perturbation results here, essentially it's just what I told you yesterday. It's a theorem of Michelin. Okay, but now we come to boundary value problems. And now it's more complicated because we have to write down this, the resolvent for a boundary value problem. And I want to do this again with an example. Yeah? Again, I take the simplest example I can imagine. And this is the directly Laplacian on the half space. So let G be Rn plus all x in Rn, xn is greater than 0, be the half space. With boundary, so the boundary of Rn plus is Rn minus 1. So if I have here the xn direction, this is my half space. And so here I have x prime, say, the first n minus 1 variables. And we consider the directly Laplacian. So consider, and I write already down the resolvent, not the instationary problem, lambda u minus Laplace u equal f in the half space, Rn plus, and gamma 0 u equals 0 on the boundary. This is what I have to solve. This is the resolvent equation in the half space for the directly Laplacian. Okay, how can we solve this? So first of all, we already know how to solve the Laplacian in the whole space. And this is the first thing I do. I solve it in the whole space. So to solve this, we write u as u1 plus u2. So I take the whole space resolvent and I subtract it from u. And now I have to be a little bit more careful. So so u1 is the whole space resolvent, but I'm living in the half space. So I first extend the right-hand side by 0. It's an LP function. I extend it by 0 to the whole space. I take the whole space resolvent and I restrict again to the half space. So u1 is defined as the restriction to the half space of the whole space resolvent applied to the trivial extension of f. Okay, so here. So first of all, E plus is the trivial extension by 0 from the half space to the whole space. The trivial extension by 0 from Rn plus to Rn. And R plus u is the restriction to the half space again. And R of lambda is the whole space resolvent. R of lambda is op lambda plus xi squared inverse. So this is the whole space resolvent. Okay, so we simply subtract the solution in the whole space. And then for the other part, we get for u2, we get the equation lambda minus Laplace, u2 equals 0 now, of course. But now on the boundary, we have some data. So this is in Rn plus. And on the boundary, this is now minus gamma 0 u1, which I denote by G. Okay, so now what we did is we simply erased this f to 0, but we have to pay a price. We have here, now we have a non-homogeneous boundary condition. So we have to solve this with non-homogeneous boundary conditions. And now comes the very traditional and obvious idea. If I'm here on the half space, I have here n-1 variables, and I make Fourier transform in these variables, not in this one. So this is what is called partial Fourier transform. So we take in tangential variables, in tangential directions, Fourier transform. Fourier transform. I will denote this by f prime, f of xi prime xn. So this is simply standard Fourier transform, but I leave one variable as it is. X prime, xi prime, and then I take here f xi prime xn d xi prime. So x prime is x1 to xn minus 1, and xi prime the same, of course. So I take partial Fourier transform. Okay, so then with this equation, and obtain. And then we get the following. We get an ODE. Yeah? The only differentiation is an xn in normal direction. This is left over. So we get an ODE. And what ODE do we get? We get this lambda from this lambda. Then here we get a plus due to a Fourier transform, xi prime squared. And the last is as it is. So d of dxn. Let's say Vxn equals 0. And on the boundary, of course, we also make a partial Fourier transform. So Fourier transform in all directions in some sense. So V of 0. So this holds in 0 infinity. It's an ODE. And the initial value is the partial Fourier transform of T. So this is an ODE. And this is an ODE with constant coefficients. So now we are in my analysis course. How to solve it? It's clear how to solve it. We have, so the first equation here has a two-dimensional solution space. You compute the roots of this. The roots is plus minus the square root of this. And so we have a two-dimensional solution space, but one solution is exponentially decaying, the other is exponentially growing. And I want to have a bounded solution. I want to have LP theory, so exponentially growing solutions make no sense. So I skip away this unstable solution. So the only stable solution of this, so let me write something down. So this, without the initial value, so this ODE, so the first equation in 2 has a two-dimensional solution space, but only one-dimensional stable solution space. But the only stable solution, stable or in the sense of bounded solution of 2 is, of course, given by V of xn. I take the exponential power. I take the part of the square root which has a negative real part, and the initial value is this one. Okay, so I have, this is the only stable solution. Yeah? Okay, this is my U2, and I go back with inverse Fourier transform, inverse partial Fourier transform, and get the solution. However, so I write it in the following way, first of all, because this is just the example, and you will see later, so I introduce some notation here. So let me write this as the fundamental solution W, depending on psi prime, xn, and lambda, times the initial value of psi prime. So this is a fundamental solution, a basis of the stable solution space, which is now one-dimensional. Okay, and therefore I can now compute U2. So U2 of x as a partial Fourier transform inverse applied to this V. So V also depends on psi prime and psi prime xn, which is a partial Fourier transform inverse applied to this W as a function of psi prime xn lambda applied to f prime g. Psi prime of dot. Yeah. Okay. And you see, we are again in the Michelin business a little bit, yeah, because we have again a Fourier multiplier, but one dimension less, and this is still a parameter. Xn is now a parameter, and I can apply Michelin with respect to the other variables. Yeah? Okay. However, for some reason, I want to write this in a more complicated way. And so I do not want to write this as simply as a multiplication operator, but now I apply the fundamental theorem of calculus, and I write this as the integral over xn with respect to the derivative of this, which first of all seems to make no sense. Nevertheless, I do this now. So this is minus the integral from 0 to infinity of the same here. If I take d over dyn, say, the same expression here, f prime inverse. Now I take w of psi prime xn plus yn lambda. And I take here f prime g tilde, say, of psi prime yn dyn. Okay, first of all, let's start with this g tilde. What is this? So g was given on the boundary only. But I extend this to a function living in the half space. So where g tilde is an extension of g to Rn plus. So it's given only on the boundary, but I extend it to the whole space in an appropriate way, of course. Okay, let's check if this is correct. So if I take the integral over the derivative, I get this expression on the boundaries. At infinity, everything vanishes because it's exponentially decaying. And at 0, I get here yn equals 0. I get here xn. And for yn equals 0, this is exactly g. Yn equals 0 means that I'm on the boundary. So this is correct. Of course, you may ask yourself, why do I do this? But before I tell you this, I continue. So I write this in a little bit different way. So we get, so U2 is, I write it as a form of two operators, so T1 of lambda applied to G tilde plus T2 of lambda applied to dn G tilde, normal derivative of G tilde, And okay, so what is T1, T2? So what I do now is I take this partial integration by the product rule. I have first to differentiate this differentiation. So I differentiate this, and in the second part I differentiate this. Yeah? So T1 of lambda, let's say applied to some phi, is defined as minus the integral from 0 to infinity f prime inverse applied to the partial derivative of my fundamental solution at xn plus yn lambda applied to f prime phi of yn dyn. And the second one is almost the same by the product rule. But here I don't have this derivative. So please note that I have included the derivative here. Okay, so this is in some sense a complicated way to write this product here, so this function here. But why is it good? Because there's a lot of results on integral operators. Yeah? So you see this type of operator, we have a combination of a Fourier multiplier in n-1 variables and an integral operator in the last variable. Yeah, so this is a kernel of an integral operator. And in the theory of R-boundedness, it's easy or possible to estimate such operators. And these operators, if you're a friend of pseudo-differential operator, this is a prototype of a so-called singular green operator. So it's a combination of Fourier multiplier or pseudo-differential operator and an integral operator. It's a singular green operator. Such operators, by the way, I don't know if someone knows this, here in the theory of pseudo-differential boundary value problems, it's the so-called Buttedemon-Welt calculus. And here we have these operators as the ingredient of the resolvent. By the way, everything I tell you here today holds in the same way for pseudo-differential operators. Yeah? You have the same description of the resolvent. Okay, so back to our situation. In principle, what I solved here now with these operators was the inhomogeneous boundary data, G. But in our situation, this G was the value of U1 at the boundary. So if I plug this in, so in our case, we have this G was minus U1, which was minus R plus R lambda E plus F. Okay, and if you look what's happening here, so I have some function here, and I restrict it on the boundary. And then this is my G. And here I have to choose an extension to the whole space. Therefore, it's very easy to define the extension by this. Yeah? So I simply omit this restriction, which is not necessary in some sense. Yeah? So we can simply take, of course, there's all other, you can also choose another one, but we can simply take G tilde as the same function, but omitting this gamma 0. Okay, and if I plug this in my solution formula, all together we get, so my solution was U1 plus U2, which was, the first one was the whole space. And then I take my solution operators T1 of lambda applied to my T tilde. So this is R plus R lambda E plus F minus, so this minus comes from here. And the second solution operator, so T1 and T2 are also called solution operators because they solve the inhomogeneous boundary value problem. And this is now applied to the normal derivative of U1, which is this one. Okay, or if you want to write down this as a resolvent. So now we have written down the resolvent. Yeah? If you want to write down the resolvent, so first of all, I define the operator. So define the LP realization. So now we are in the half space. So the domain of this are all functions in W2P Rn plus Sobolev space of second order, which have zero directly boundary values, directly data, as a subset of unbounded operator in LP, and of course LPU is Laplace U. And then we can write down the resolvent. It's already written here. So we have an explicit, more or less explicit description of the resolvent. So then lambda minus AP inverse is R plus R lambda E plus minus T1 lambda applied to this R plus lambda E plus minus T2 lambda applied to dn R plus R lambda E plus. And if you never heard about the Boutté-de-Monvel calculus, today this is the first step of Boutté-de-Monvel calculus, solving boundary value problems. Okay, so we have here, now let's check these operators. We want to estimate lambda times the resolvent. So we have lambda times this resolvent. This is R-bounded, we already know. This is a whole space resolvent. This doesn't matter. It's independent of lambda. Again, we multiply by lambda, so we have here again this lambda times the resolvent. And now we can show, and this is what I do not do in my talks, that this is also R-bounded. And this is a little bit more machinery than I told you yesterday. It's not so easy, because you have to consider these integral operators. But R-boundedness and integral operators behave quite well. So one can show that T1 and T2 are also R-bounded. And this is the reason why I write it in form of integral operators, because if I integrate, in some sense, I average R-bounded operators, it's still R-bounded, so integration is some kind of averaging. And this is one of the general statements, which was invented at 2001 to 3, say. So one can show that these operators are also R-bounded. But this is not within the scope of my talks, it's too long. That T1, T2 are R-bounded operators. We know already, that lambda times the resolvent, whole space resolvent, is R-bounded. And altogether, this is the aim to show, this is the way to show thus we get that lambda times lambda minus AP inverse is R bounded. And therefore, the Dirichlet Laplacian has maximal regularity. And again, there's no need to shift. So in this situation, so the Dirichlet Laplacian is in 0 MR 0 infinity LP Rn plus. Okay. So this was the simple example, but this I made it a little bit lengthy. I hope to explain it, because if you understood this example, you understand the general situation as before. So this is a way how to solve boundary value problems locally, model problems in the half space. And this can be generalized now. And what is the essential point? The essential point in this proof is this fundamental solution here. So we want to solve this boundary value problem, number 2. And for this, we need the fundamental solution. We need unique solvability of 2. This is the point, which was the case here. But this is the condition. Unique solvability, so we can write down with some fundamental solution. Here, the solution space is one-dimensional. In general, it will be higher dimensional, so we need unique solvability of this ODE. And this is exactly, again, a very classical definition of parabolic boundary value problems. The unique solvability of this ODE. And if we have this, the whole thing which is written here holds in the same way for general boundary conditions, arbitrary order, arbitrary boundary conditions. Okay. And so for the general case, we need the following definition. So now I consider again the general situation. A of xd, bj of xd, be as above. And then there's a notion for this. So now I assume that A is already parameter elliptic. Let A be parameter elliptic. Now the question is, what about the boundary operators? And there's we say that the boundary operators satisfy some condition. Then we say that the so-called Shapiro-Lopatinsky condition holds. If the following is satisfied. So I have to be a little bit careful here. So Shapiro-Lopatinsky is a local condition. So now I'm living in a domain. So I have some domain G. I have some x naught on the boundary. And then first of all, I choose a coordinate system according to this. So let x naught be on the boundary. Let xi prime lambda be in Rn minus 1 cross x at 0. Now I choose a coordinate system. Choose a coordinate system. I take the original coordinates, but I simply translate and rotate by translating and rotating the original one. So I simply choose, in some sense, the direction such that the xn direction is here the inner normal, such that the xn direction is the direction of the inner normal. And so we make it in some sense, we consider this as a half space. And I freeze again the coefficients. Yeah. So it's constant coefficients considered in this half space obtained by rotating. And then we get the following ODE system. Then the ODE system. Okay, so now I take lambda minus principal symbol. So I take only principal parts. I freeze the coefficients. I take partial Fourier transform, and I still keep this minus I dxn as before. So I do nothing in this direction. V of xn equals 0 for xn greater 0. And this is now an operator of order 2m. And I need half of the order as boundary conditions. So I take again the principal symbols. I freeze the coefficients. I take partial Fourier transform. I keep the last as it is. And at xn equals 0 is, say, gj, for j from 1 to n. Say 3. As for every right-hand side, as for every g1 to gm in Cm, this is just numbers, a unique bounded solution. Yeah. This is Shapiro-Lopatinsky. And the idea is exactly the idea of this example. Yeah. So of course I localized, I omitted lower order terms, and I've written this in such that this is xn direction. So in these coordinates, but then it's exactly the same idea. So then I'm in the model problem of the half space again, and I make partial Fourier transform. Okay, and if this holds, if this condition holds, if this holds, we say that the boundary value problem A and B is parameter elliptic. That A, B1 to Bn is parameter elliptic, or dt minus A with these boundary operators is parabolic. Okay, of course, to check if some given boundary operators, some given boundary value problem satisfies this condition, you have to solve this ODE. Yeah? And with my experience, this is in some sense really necessary. Yeah? There's no simple description. Of course, standard boundary operators always satisfy. For instance, Dirichlet operator, if you have Dirichlet boundary conditions, then this, and you have a parabolic operator A, then this is always satisfied. The same for Neumann. Yeah? The same if you have an operator of higher order and you have what is called generalized Dirichlet boundary conditions. Yeah? So, for instance, if you have an operator of order 4, like in the plate equation, and then you consider, then the Dirichlet boundary condition means u and the normal derivative equal to 0. Right? You need two conditions. And this is always satisfied. So there are some There are some results on boundary conditions that this is satisfied, but to my knowledge, it's not known. There's no classification of all boundary operators which satisfy this condition. It's really unclear. And for instance, if you consider systems, we have similar definition, of course, for systems. My equation is scalar, but if you have systems, then almost nothing is known about this condition. This is a really hard problem. But in many applications, you can check this. Yeah? And many standard boundary conditions satisfy this automatically. Okay, and now, if I have given such a boundary value problem in some domain and define, as usual, AP by now the domain of AP is all U and WP2M of G, where all boundary operators vanish. And the operator acts as A, of course. And then we can make essentially the same as before. So we can, first of all, we can write down the solution operators. Yeah? And this is what I want to write down here. So this is the theorem. So I still stick to Rn plus in this formulation. So locally, it's a local description of the solution operator. So I take the model problem. A, B1, Bm, xd, B parameter elliptic in Rn plus. And I assume they have constant coefficients, and I assume they have no lower order terms. It's constant coefficients. And without lower order terms. So this is a so-called model problem. And then I can make essentially the same idea as in my example and write down the solution operator. Yeah. So then the statement is the following. Then so C plus without 0 belongs to the resolvent set of AP. So this is uniquely solvable for all lambda in the right half plane. And the resolvent is given by, now comes almost the same expression as before, so lambda minus AP inverse. So I start with the whole space resolvent. And now I have a sum from 1 to m of solution operators T1k of lambda. And now we had here just the resolvent. But why did we have the resolvent? Because we had on the right-hand side of our boundary value problem, we had U1, the value of U1. But this was just a directly boundary conditions. And in general, so we solve in some sense lambda minus A U2 is 0, and Bj U2 is minus Bj U1 now. And therefore we have this here. And therefore now appears not only the resolvent, but the boundary operator applied to the resolvent. R lambda E plus. And then we have the same again with a second solution operator. And now we have, again, bk x d normal derivative, additional derivative, r plus r lambda e plus. Okay, so what are these operators? What are these solution operators? So first of all, here R of lambda is the whole space resolvent. Resolvent to A of xd. And these operators are defined in the following way. So the first, we have an index k running through boundary conditions. So applied to some phi of x, defined as minus 0 to infinity, partial Fourier transform inverse. And then I take the normal derivative of the fundamental solution wk at xi prime xn plus yn lambda applied to f prime phi xi prime yn dyn. And the second is almost the same. But here I have no normal derivative. And what are these wk? So, and for k from 1 to m, this wk is the fundamental solution of the ODE. Wk of xn, wk of psi prime xn lambda is the solution of the ODE, which appears in the Shapiro-Lopatinsky condition. So A0 x naught psi prime minus I dxn wk of xn is 0 for xn greater than 0, and the boundary conditions Bj0 x naught psi prime is I dxn wk xn xn equals 0 is delta kj. So I know this is uniquely solvable for every right-hand side. I take the Kronecker symbol on the right-hand side, so a unit vector on the right-hand side, and I get a basis W1 to W2M, a basis of the stable solution space. And this solution is the symbol of my kernel operator, of my integral operators. It's the kernel of the integral operator. And so some remarks here. Okay, maybe some words on the proof. Idea of proof. So essentially, this is of course the same as in this example. Yeah? But one particular point. So it's connected with a number of boundary conditions. Yeah? So if you have an operator of order 6, maybe probably you never have such an operator, but whenever you meet an operator of order 6, you know you need 3 boundary conditions. And why? Because if this is parabolic, if A is parabolic, yeah, then one can show, so if A is parameter elliptic, and n greater or equal to 2, one can show that this ODE, to solve this ODE with constant coefficients, I have to compute the roots of the symbol with respect to this variable. I consider this a polynomial. And this is a polynomial of order 2m. So it has 2m roots. And one can show that half of the roots are below and half of the roots are above the imaginary axis. So, or maybe the real axis, it's with this I. Yeah? So the roots are split. So the stable solution manifold and the unstable solution manifold both have dimension m. Yeah? Automatically, yeah? One can show that, let's say, for the stable solution space of 4 has dimension m. And this is in some sense also the idea of parabolicity, yeah? To have so we have that. So the proof of this is a simple homotopy argument. Yeah? So by symmetry in some sense, yeah? Automatically. Yeah? Therefore, to obtain a unique solution, I need m boundary conditions. Yeah? So therefore, we need m boundary conditions. Conditions for a unique stable solution. And this is the reason why I need half of the order of the operator as boundary conditions always. By the way, I'm telling you here the very simple prototype. Yeah? Still, it's a general boundary value problem, general operator, general order. But what also happens is that you have not a boundary value problem, but a transmission problem. So you have the equation not in half space, but in the whole space. And you have 2 equations on the left and right hand side, and you need continuity or something like this as a transmission condition. And if you have operators of order 2, left on the right hand side, then you need 2 transmission conditions. So in a boundary value problem, the order of the number of boundary conditions is half of the order, and transmission conditions is equal to the order to get it well posed. Okay, but this was just a side remark. And then the remainder, it's exactly as in the example. Yeah? We subtract the whole space solution, and then we solve the ODE. We know here the basis, and then this result, this theorem can be shown exactly as in the example. Okay. Okay, now we know the solution operator. So maybe I add some remark here. If you look what we have done, we did not only solve the resolvent problem. No, we solved inhomogeneous boundary conditions. No? We wrote down the solution operators for inhomogeneous boundary conditions. Yeah? So we have defined the solution operators for inhomogeneous boundary data. Which means we can now solve, with the same solution operators, of course, we can solve say lambda or say dt, doesn't matter, u equal f in G, and b j u equal gj, j from 1 to m on the boundary. In our situation, we have defined the solution operators for G, and we applied it to the resolvent. But of course, you can have an additional data, and we know the solution. And so with this method, we can immediately write down this boundary value problem as a mapping to the appropriate spaces. So we have shown. We have not yet shown maximal regularity, but this will come. So we have shown maximal regularity. Oh, here it's written in the resolvent setting. Yeah? So we have a lambda of the mapping in the sense of invertibility of the map dt minus a b1 to bm, which maps our solution space, which was this E, to F times. And now we have, now the question is, what are the spaces for these right-hand sides? But this is what I answered in the first lecture. The spaces are trace spaces on the boundary. So let's say the product j from 1 to m of gamma mj, trace spaces of order mj, because this is the order of the boundary operators of E. And these are trace spaces on the boundary. Maybe to be a little bit more precise, I would say. Let me here, because I did not prove it here, and I don't want to have an initial of this one. Okay. If I take the instationary problem, I still have to add, of course, the initial value. But again, we have, so the idea of this resolvent description is more than only the resolvent. The idea is to have a mapping in completely inhomogeneous right-hand sides. I have, for the instationary problem, I have non-zero initial value, I have non-zero boundary values, and I have a non-zero right-hand side, and I can write down the solution operator. So I'm shifting a little bit away from operator theory, semigroup theory. I consider the inhomogeneous problem. And this is also a little bit generalized notion of maximal regularity. Maximal regularity in the sense of isomorphism of Banach spaces. But this was just a side remark. I don't want to go into detail here. But this was the reason why I told you about the trace spaces in the first lecture, because these are the spaces for the right-hand sides, and we know the solution operators. But now we have, I continue in this to this theorem, now we have the description of the resolvent, and now we use the machinery of R-boundedness to show that this is R sectorial. So we have the following final result here. So let A B1 to Bm be parameter elliptic in G. Now again, general domain. And then there exists then there exists a lambda 0 greater than 0 such that AP plus lambda 0 is R sectorial. In particular, A itself has maximal regularity. In particular, AP has maximal regularity. On finite time intervals. And the idea of proof is the same as before. So, idea of proof. So for the model problems, we know it in the sense that I told you that these operators are R-bounded. And for if we are not in a model problem case, we again make a partition of unity. So either in this partition of unity, either we're in the interior of G, or then we are dealing with the whole space as a model problem, or we're on the boundary of G, or then we have this resolvent description. So for the model problems, this follows from the R-boundedness of lambda times the resolvent, whole space resolvent, and of the solution operators, T1, K, lambda, T2, K, lambda. And the general situation is again dealt with a partition of unity and perturbation results. Okay, so as before, I construct local resolvents for operators which are locally close to our given operator. And then I put them together by a partition of unity. I sum them up. Then I do not get the real resolvent, but I can show I get something which is close to the real resolvent. And at the end, it's a Neumann series argument. And a final remark. Maybe, of course, I've hidden here a lot of technique. Yeah? The technique is here, perturbation results. Yeah? This is, it's not so easy. Yeah? And if you don't want to localize all the time and make a partition of unity, then you move over to the theory of pseudo-differential operators. Yeah? So this localization, this is the idea of pseudo-differential operators to have a global calculus. Yeah? So remark. So the idea of pseudo-differential boundary value problems. This is the Boutté-de-Monvel calculus. Is to avoid localization. So I want to obtain it without localization and there's in fact a machinery of X-dependent symbols, boundary value problems, where I can, on some manifolds, say, with boundary, where can I simply apply the theory of pseudo-differential operators and get the same results, the same resolvent description for pseudo-differential boundary value problems. And this was, as I said, again, invented around the 60s. 60s, 70s of the last century, at the same time where this was invented. So this was the idea of pseudo-differential calculus by Hermander, for instance. Yeah. Okay, with this remark, I would like to stop and thank you for your attention.